Welcome back. This is the day the Lord has made. Let us rejoice and be glad in it. In this video here, I'm going to talk about enthalpy and changes in enthalpy, as well as calorimetry for my chemistry class. So enthalpy is this idea of like how much energy is inside of something. For the sake of our class, it's primarily just thermal energy. When you get to your future chemistry classes, it also will include work done by the chemical. Like, so if a gas is being generated, it has to make room for itself. So it's also, it's total internal energy, but for our case, we're going to focus on enthalpy as just being thermal energy. All right. Now, we're going to denote enthalpy with the letter H. So don't ask me why. Someone chose letter H for enthalpy. So, and actually, when we talk about enthalpy too, and internal energy, we should remind ourselves that enthalpy and energy are something we defined. We didn't get some book from God that said, hey, here's what unit you should use for energy. This is what it is. We defined energy and we defined these things. And so what we did is we pretty much said, let U be this, and then everything else based off that. Now, again, for most things, we just chose water. We said, okay, like for example, the calorie is pretty much just based off of water. The specific heat of water is the same as a calorie. So again, a long time ago I said, well, what does everything have? Water. Let's define energy needs for a warm-blooded person like ourselves based off of water. So now we have joules. So things have changed a little bit, but for the most part, we still use something as a point of reference. All right, so anyway, change of enthalpy is what we were looking at. We define something and we find out how does it change, how much energy does it take to go from this to that. So you can associate, again, since we're talking about enthalpy and associating with like thermal energy, you can associate H with a positive H being endothermic. So positive H means we're increasing the internal energy. We're giving more thermal energy. So a positive H means that we've put energy into the system. That's endothermic. A negative H is going to mean that we have had energy leave the system. So that's going to be exothermic, energy exiting the system. And again, this comes down to just like chemical reactions where atoms are changing bonds. So again, big idea from first semester, if you break a bond, it takes energy. You form a bond, it releases energy. And whether you're endothermic or exothermic comes down to which one took more, which one is bigger. If you spend a lot of energy breaking the initial bonds, then you're going to have an endothermic reaction. If you break weak bonds and make strong bonds, that's exothermic. So anyway, enthalpy formation values are basically what we use to calculate unknown reactions. But so like then enthalpy formation, this means energy to form this substance. How much energy does it take to form this? Again, we need points of reference. And so we pretty much said anybody that's in its standard state. What does standard state mean? On the periodic table, what state of matter are you supposed to be? So iron, he is a solid. He's supposed to be a solid. That's considered standard state. So iron, be a solid. How much energy does it take for iron to be a solid? 0. Helium, be a gas. How much energy does it take for helium to be a gas? 0. So those things are in their standard state. If you're composed of multiple elements, you're not in your standard state, because this is just based off the idea that everybody has to be in just their individual element. So with the exception of diatomic stuff. Okay, so and this is just a point of reference. We had to define something as 0 for energy. We said, hey, let's just use the scratch elements, an element all by himself, and how they're supposed to be as 0. So yeah, and how much energy does it take for gold to be a solid? None. So because it is already supposed to be a solid. So for those who care to know too, it's also at 1 atmosphere and 25 degrees Celsius, pretty much meaning that when you look at the periodic table, normal room conditions. All right, so it's not based off of a different temperature, or a different pressure. It's just right now approximately what would it be. So only elements. So like water, which is composed of hydrogen and oxygen, is not 0. It's a combination. So, but you will find those things on the chart. Excuse me, this won't have a 0. So, because those things, when you have a molecule or compound, it's making them from scratch. If you took the elements from their standard state, so like carbon dioxide would be, well, what if we take carbon and oxygen, both in their standard state, carbon as a solid, oxygen as a gas, put them together, we get some value. So this is saying that, hey, we have energy change of negative 393.5 kilojoules per mole. And this is also per how much you're making. So if you're making more than one of these, it'd be twice as much if you had 2 of them. So if we made 2 CO2s, we'd get 2 moles of this, we get 2 times this. Another example, how about hydrochloric acid's enthalpy formation value? Well, we just mix hydrogen gas with chlorine gas, and this would be the enthalpy formation of HCl. So All right, so just a little review here for us. Which of these guys are not in their standard state? And if it isn't, does it have an HF that is positive or negative? So again, when we think about HF being positive or negative, do we need to put energy into it? If we need to put energy into it to make it this could be a positive H. That's endothermic. If we're going to take energy away from it, that's going to be a negative HF. So chlorine as a gas. Is chlorine supposed to be a gas? Yes, it is. So is it supposed to be diatomic? Yes, it is. So he's supposed to be 0. Potassium. Is he supposed to be a solid? Yes, he is. Sodium is supposed to be a solid? Yes, he is. Argon is solid? No, argon is a noble gas. Argon is supposed to be a gas. So typically, argon is supposed to be a gas. And if we want argon to be a solid, is this going to take energy or take energy away? Well, if we want to take gas and turn it into a solid, we got to take energy away from this thing. So this could be a negative H for argon as a solid. So we're giving energy away because argon used to be flying around. Now it's not. So again, a big idea too, if you're going towards a solid, energy is exiting because the molecules stop moving. If you're going to solidify, you got to stop moving. If you go towards a gas, we got to put energy into it. If you want to boil water, you put H into it. So anyway, argon is a solid, that would have a negative H on the for its HF value. Next row, oxygen is gas? Yes, supposed to be like that. Bromine is a solid? No. Bromine is a solid. Bromine is supposed to be a liquid at room temperature. So we're not going to let it be liquid, we're making them a solid. To do this, we got to take energy away. So this bromine here would have a negative H as well. Mercury is a liquid? Yes, mercury is supposed to be a liquid. Sulfur is supposed to be a solid. Next row, sodium's not supposed to be a gas. So normally sodium is a solid. If we want sodium to be a gas, what do we got to do? We got to put energy into the sodium. We got to heat it up, and so it turns into gas. So this one has a positive H. We had to put energy into it. So if we had a chart which had all the enthalpy information values, sodium as a gas would have a positive value. Lithium is supposed to be a solid. Fluorine is diatomic, supposed to be a gas. Krypton is supposed to be a gas. Silver is supposed to be a solid. Gold is supposed to be a solid. Here we have O, not O2, just O. Since oxygen is supposed to be diatomic, this is not standard state. Now, if you want to take oxygen and pull them apart from another oxygen, this is going to take energy. Because anytime you break a bond, you got to put energy into it. So if you see something that's supposed to be diatomic and they're not, and they're only a mono atom, that's going to be a positive H. You got to pull that thing apart. So here we just have mercury in 3 different states. Again, mercury as a liquid is supposed to be 0. His H value is 0. But the gas one, we got to put energy into it to make it become a gas. To be a solid, we have to take energy away. So if we had a chart, we'd have these 2 things next to each other. The Hg as a solid would have a negative value. Hu liquid would be 0, and Hg as a gas would be a positive. So again, maybe real quick, come down here. So again, these charts, if you ever look at them in real life, they're just huge, ginormous, because they'd have every single substance that could possibly exist and say, hey, what's the change in energy to get there? So as you look at this chart, say, oh, Ag is supposed to be a solid, 0. But if you have Ag and Cl come together, it's got some value. And so every single time you find someone who's our scratch element, it's 0. And negative or positive just tells you how much energy it's going to release or it's going to be required to make it from scratch. Some of these are pretty large. So let's see. Anyway, I won't bore you looking at that any farther. So, all right, so then we want to find a change for a reaction. Like what if we have a chemical reaction and we want to find the change energy for the reaction? What you do is you use those values from the chart below. Basically, what we're going to do is say, okay, well, how much energy are we going to form by making the new products? So that's going to be a change in energy by forming those. Again, when we form something, that is releasing energy. So back to like reaction coordinate diagrams, this is going to be the fall. So you go up the hill and down the hill. On the way down, you're releasing energy as you form compounds. Then we're going to take away the energy that it took to break apart the original. So we subtract off their reactants enthalpy values because we're going to undo them. So rather than forming them, we're breaking them, and so that's why we subtract it. And that'll tell you the change in enthalpy for that reaction. So sample question here for us. What if we want to have methane burn with oxygen to make water and carbon dioxide? The way you'd figure this out is you would go to the chart below and find their values. I don't know if this chart has these values on here. Let's see. Oh, there we do. CH4 as a gas, negative 74.81. Up here, just rounded up to negative 75. So we're saying that on the chart, if we form CH4, it has a negative 75 kilojoules of energy being released. Again, that's the idea. If we take carbon a solid, mixed with hydrogen and gas, it would end up releasing this much energy as we form CH4. But since this is a reactant, we're not actually forming it, we're breaking it apart, which is why, again, we would subtract it because we're changing the sign. Again, oxygen by definition is 0, so we're just going to take his value, and it doesn't matter, even the balanced equation here doesn't matter because it's just times 0. We're making 2 waters as a liquid. Each one of those will have a negative 286 value. Every carbon dioxide is negative 393. So we have negative 75 on the left side, our reactant side. We have negative 965 on the right side. Products minus the reactant value will be the change in energy. Now this is for this reaction. This is per mole. So if we burned 1 mole of CH4 as a gas, producing this over here, we'd get this much energy released. If we burn 2 moles of this, we get twice as much. If you burn 3 moles of this, you get 3 times as much. Okay? So again, important equation for you is right here. Pretty much when you get to some of those questions about calculating enthalpy changes, you just take the value, their enthalpy formation values, multiply them by the coefficient, take the products values, subtract the reactant values, and that's going to be your change in enthalpy. You don't need to memorize these numbers. The only ones you're expected to know are things like standard state that are 0, or if I give you an element, you should be able to determine whether it's a positive or negative or a 0 value. It's 0 if it's standard state, it's positive if you had to go up towards gas, and it's negative if it's in standard state liquid and you want to be a solid, you got to take energy away. Also, some of the questions you'll have to solve will make you standardize it per mole. So I'll give you information using calorimetry kind of stuff like specific heat and heat capacities to find out, well, what is the change in enthalpy per mole? All right, so calorimetry, this is the idea of just like finding the change in enthalpy. So enthalpy is the amount of energy in it, and calorimetry is how we figured it out. It's just a word we said, we're studying the calorie. So again, just like its name says, calorimetry is finding the calories inside of it. Again, a lot of application towards like food we eat, how much is inside there. You know, the dream job in chemistry is to be the bomb calorimetrist. All you do is you take some food, blow it up with some oxygen, and find the change in energy, and then you put the food label on saying, this food has this much energy. Like, oh yeah, we burned the Big Mac, and the Big Mac, when we burned it, gave off this much energy. So here's how many calories are inside the Big Mac. All right, you just get to blow food up all day. So the way they do it, they just have this like high concentration of oxygen with high pressure. They put the food inside of it, and then they have a little spark goes off and food blows up, and then the heat of the calorimeter, which is the thing that absorbs energy, just heats up, and then we know how much energy is inside of it. So you do need to take note that when we're talking about calorimetry, sometimes we talk about heat capacity and sometimes we talk about specific heat capacity. They're 2 different things. Heat capacity is the energy for the change for the whole substance, ignoring the mass, although it's part of it. So not totally ignoring it, but we're saying the heat capacity is already taken into account the mass. Specific heat is per gram. So when you're doing some calculations with calorimetry, keep an eye on that. Is it asking for a heat capacity or a specific heat capacity? So let me talk a little more about that. So Mr. Love and his kids, we have the same specific heat. We're both big bags of water, so we have roughly the same specific heat. But I'm a bigger person, so I have a larger heat capacity. It takes more energy to change my body by 1 degree. It takes less energy to change my kid's temperature by 1 degree. So the bigger you are, the larger your heat capacity, and the smaller you are, the smaller heat capacity is. Cross-country runners, they don't usually get overheated real well, but they can get cold quickly if they stop running. Because if you're a smaller body, you can get cold quick because you don't store a lot of energy. If you're a big body, you might have a hard time cooling down, but you don't get cold. So for calculating these things here, again, we've seen this before. Specific heat is just energy divided by your mass times change temperature. Your change temperature can be Celsius or Kelvin, doesn't matter which one you use. Heat capacity looks the same, except we don't have mass on the bottom anymore, but it takes into account. So let's do a quick calculation of those things, and then we'll be done with this video. So a calorimeter has a heat capacity of 15,000 joules per Kelvin. So we're saying how much energy the calorimeter can store before it changes temperature. We burn a small piece of food in the calorimeter, and the food, while it's burned, releases this much energy, 300,000. How much does the temperature of the calorimeter rise? So again, the calorimeter can store energy at this amount, 15,000 joules per Kelvin. We've given it this much energy, so what's the change of temperature? 15,000 joules per Kelvin. This means it takes 15,000 joules to change the temperature by 1 degree. We know that every 15,000 then it absorbs, it goes up by 1. So we have the total energy divided by the heat capacity, in this case, just the change in temperature. So it would change by 20 degrees because the first 15,000 joules that we absorbed is going to raise by 1 degree. The next 15,000 is another degree, and so on and so forth. We could take a specific heat and turn it into heat capacity. So my kids, this is probably like Abigail's size. So she has a mass of 20,000 grams. And if we're going to talk about Abigail, her body has this specific heat, 3.5 joules per gram. Now, again, it's not water because humans tend to be around 3.5 because even though we're mostly water, we also have some like metals inside of us which have lower specific heats. Regardless, what is my kid's heat capacity? And what that means, how much energy would Abby have to gain or lose to change a degree? So to find this out, since we're given her mass, we know, and her specific heat, we're saying that every single gram is going to cost us 3.5 joules. So if I want to take 1 gram of Abigail's 20,000 grams and heat it up by 1 degree, it costs 3.5. But we're not just doing 1 gram, we're doing the whole body to find the whole heat capacity. So 3.5 joules per gram per degree, and we're heating 20,000 grams up because that's her whole body, and just 1 degree, 70,000 joules. That'd be heat capacity. That's how much energy she would either gain or had to release to change by 1 degree. So what this means is if she absorbed 70,000 joules of energy, her body temperature would rise by 1 degree. If she lost this energy, like if she went outside without a coat and was cold and she lost 70,000 joules of energy, she would cool down by 1 degree. So, and last note real quick, calories, again, you probably have seen this before. Every calorie is 4,184 joules. That's the big calorie. The small calorie is 4.18. They're only different by a factor of 1,000. So again, the original calorie, the lowercase calorie, was defined as water changing temperature. And because we're a really big bag of water, we defined one based off of like per 1,000 grams of water so that we'd have a more reasonable number to talk about. So rather than having a 2 million calorie diet, we have a 2,000 calorie diet that's supposed to be taking place. All right, God's peace.